the conditional CDF of x given y is defined as after all. So, this is the definition. Okay. So, the denominator is exactly what you predicted and the numerator is actually also exactly what you predicted, right. You are just integrating over the x variable, right, the x variable of the joint density. Okay. And this is exactly what this is, if you send delta to 0, right, that is what this is, correct. Fine, but this is the definition. So, the one approach you can take is that this is my definition and do not ask any further questions, right. So, you can verify that this has the properties of a CDF in the sense that, I mean, if you put x is equal to infinity you will get 1, x is equal to minus infinity you will get 0, it has right continuity, etcetera, right. But what I informally wrote down there is what motivates this definition, right. You essentially what you do is condition on y lying in some interval, okay, small interval. And so, if this is the conditional CDF, then I can write a conditional PDF of all this x given y is defined as little f x given y of x given y is equal to. So, this see this is like a CDF and it is looking like integral minus infinity to x of something, right. So, what is inside must be my conditional PDF, right. So, it is a very natural definition. X comma y over f y of y. Fine. So, it has a fairly intuitive form finally. So, although this was a bit of a problem to define it correct, I mean define it precisely, you are back to the form where you have the joint PDF over the marginal PDF, which is happy news, which is good news, right, which is. So, this is exactly similar to what we had for the discrete case, except in the discrete case what is on top and what is on bottom were actually probabilities. Here these are not probabilities, these are densities, right, these are densities which have nothing to do with probabilities, right, only if you integrate them you get probabilities, and this is defined whenever the density is non-zero, correct. Then finally, I will just make one more definition. So, the conditional probability of an event A given y is defined as, see so far I have defined So far I have defined the so this is the joint CDF, right. So this is the probability of the event that capital X is less than or equal to little x given y equal to y. Now I am talking about some generic event in the sample space, it may not be x less than or equal to x, it may be something more complicated. So it is defined as follows: probability that, so I am looking at the event x belongs to A, right. This A is so this is well, this is not really an event in the sense that, so what should I say, this is some probability of some Borel set actually. So maybe I should not I should not say it is an event. So let me write this down and let me think about what to say there. Probability of x belongs to A given y equal to y is defined as integral over A f x given y of given y dx, okay, which is again nothing but the indicator of A so I should probably say the conditional probability of the event x belongs to A, right. This A is some Borel set, the Borel set on R. So this I can write as f x given y of I A of x. Okay, this is the definition of. So here the CDF only gives me the event that x is less than or equal to x, but I can now talk about x lying in any Borel set, right. If you want, if you do not like A, you call it B, A is just a Borel set. Okay. It is given by the integral over that Borel set of my conditional PDF, which is again defined to be the integral over the whole space, whole real line of the indicator function times the PDF. Okay, this is also by definition. Okay, any questions on this? So let me do an example. Okay, so I will do some very simple example. So let us say let us take a following distribution. So this is, so let me define the joint PDF. Yes. Yeah, so this f x given y is exactly this. So you can put this guy here, joint over marginal, right. This we have already defined. See, this is like a density, conditional density. So you integrate the conditional density over any Borel set, you will get the conditional probability, that is it, right. Okay, so the example I am talking about, so let me just make some example where, so I have some uniform distribution in this. Okay, so let us say that is 2, that is 1. Okay, so in this triangle, so my here I will have, I want a uniform density on this, which means f x y of x y must be equal to 1, isn't it, right. The area of this triangle is 2, yeah, so it should be 1, right, for x y lying in this inside this triangle and 0 everywhere else. So, that is why. So, I have described my what is this joint probability density function. Okay. Now, I want to define. So, now I want to obtain the marginal of x, marginal of y and conditionals. Okay. So, if you want to let us say get f y of y, okay. F y of y will be the integral of f x y of x y, which is simply 1, right, 1, and you have to integrate with respect to the other variable which is x, right. So, this will be 1 dx and x ranges from. So, x ranges from 0 to 2 minus 2 x or what 2 minus 2 y, right. So, what is this line? This line is 2 x plus y equal to 1 or the other way around, 2 x plus y equal to 1, this is the line, right. So, if I fix, so I am fixing and I am integrating x, right, fixing a y, I am integrating over x. So, here x should vary from 0 to 1 minus 2 x, no 2 x plus y equal to 2, you are right, 2 x plus y equal to 2. So, which means I should vary my y from sorry x from 0 to 2 minus 2 x, correct. So, I should sorry. So, yes. So, I should vary. So, this should be something in y, right, you are right, sorry. So, what should this be then? 2 minus y divided by 2, 1 minus y over 2, agreed, fine with me. So, this is correct. See, I don't this kind of stuff I do not do it correctly often. So, so this is equal to simply 1 minus y over 2, okay. And y vary, what is the range of y now? Again 0 to 2, this is for 0 less than or equal to y less than or equal to 2. So, that is your marginal PDF. So, how does the marginal PDF look? So, if you plot this guy, if I am plotting f y of y, it varies from 0 to 2, the y varies from 0 to 2, and at y equal to 0 I have 1, then I have like that, right, is not it. So, now I am plotting. So, this is a plot, see this is simply the x y plane, but this is a plot of the density of y, and you can see that this is a valid density because integrates to 1, okay. So, why do you think so? It looks as though, so y is more likely to be closer to 0, right. I mean that is because there is, even if you fix, so whatever, so if you just look at this y, there is more mass coming in from here, right, closer to 0, which is why it is looking like this, okay, well and good. Marginal of x can also be easily computed. So, what is f x of x? The same thing, integral 1 dy, I have to integrate, now I have to do it the other way, right, 2 minus 2 x 0 to so now okay, so I was computing f x back then. So, okay, so that should be 2 minus 2 x, good, over x in 0 1, right. So, that looks like that is 1, and at x is equal to 0 I am at 2, then I will go down like that, right. That is my this is my marginal PDF of x. Now, from this you can ask, are x and y independent? See, if you multiply the marginals 2 minus 2 x and 1 minus y over 2, you do not get the joint. So, they are not independent, x and y are dependent. Okay. So, now suppose you want to compute conditional PDF. So, I have f x given y of x given little y is equal to f x y of x y over okay. And this should be equal to, so this is 1 whenever it is, if x y is in the appropriate the triangle, this is 1 divided by f y of y, which I computed as 1 minus y over 2, right. So, that is simply 2 over 2 minus y. And this is valid for for what range? See, y, see here y is some fixed number, right, and x, this is for x varying from x in 0 to, so this is for x belonging in 0 to 2 minus, so 1 minus y over 2, isn't it? Is that right? Yeah, correct. Yes or no? Did I make a mistake? f x y, so f x y x comma y is equal to 1, that is my joint, alright, and I am dividing by my marginal of y, which is defined for, so y is between 0 and 2, right, but I am fixing a y, alright. So, I fixed a y, and so my x should, so my x can only be between 0 and 1 minus y over 2, correct. So, what kind of a distribution is this? Yeah. So, this is like a uniform, right, isn't it? So, this is like a uniform, this is conditionally uniform, yes or no? Fine. So, see, remember this y is a constant now, you have fixed y, it is not a function, right. So, this is a, so although, so the f, so I want to make this perfectly clear, what you are computing is actually a function of x. On the right side there is, see, of course, this will contain, this will be dependent on y, right, because you are fixing a y, the answer will be a function of y also, but this is actually a function of, the function you are computing is that of x, right, and there is no x here, which means x is only in the constraint, x is implicit. So, this is constant in x, correct. So, I hope I did not make a mistake, I think this is actually correct. right. So, you have a uniform distribution in 1 minus y over 2 if you fix a y. So, does that make sense? All right. So, what this is saying is if you fix a little y plus delta here and look at how x is distributed, it is in fact distributed uniformly, and that makes sense because in that little rectangle or whatever that little strip, your after all the original thing is constant, right, original f x y, the joint PDF is constant. So, what you expect and say that strip is should be constant, and it is constant, except you have to know what constant it is, right, it is that constant. Okay. Similarly, you can figure out the opposite curve y given x. So, that will be 1 over that guy, and that is also uniform, right, correct. So, everybody is with me that this is a uniform random variable, conditionally uniform. The intuition is just what I said, just to blow up that figure. So, you have that figure. So, you have 2 1 x y, sorry, so this is y x, you have f x comma y equal to some constant 1, right. Now, we are fixing a y and looking at the little strip, right, you are looking at that little strip y plus delta, and you are looking at how x is distributed on that strip, of course, and you are going to divide by f y, right. So, on that strip it must be uniform because what you started with is a uniform in the first place, correct. Are there any questions? So, you can do any number of examples now, right, you can give yourself some homework, take x any joint distribution you want and compute all these conditional PMFs and marginal PDFs, sorry, conditional PDFs. Okay, if there are no more questions, I will stop.